Okay, so next time. Last time we saw that G is a group and N is a normal subgroup of G, then G on N is a group by the following law. Okay, if A and B are in G, A and B and it's A B. Okay, so and the set G mod N in this case is called a quotient group. Okay. Okay, so the set G mod L is called the quotient group in this. G modulo N. Okay, great. This is just a small notation. Now we'll start. Study called the symmetric and alternating. Now let us remember some facts on the symmetric group. So let us end the symmetric group on n letters that I assume to be 1, 2, 3 up to minute. We call an element sigma Sn. It's called permutations. Yeah. Did you ever use this word? Did you ever use the periodic permutation? No, but yeah, exactly. So what you're doing is you're just permuting n letters, right? You're just permuting. Okay. Any or a cycle of length k is of the form A1, A2, up to AK, where the AIs are distinct. Call this a K cycle technically. Call this a K cycle. For example, 1, 2, 3 is a 3 cycle. Okay. Now a cycle of length, a K cycle has order. Has order K. I'll let you check that. A K cycle has order K. Check this. Not that bad. The inverse of a K cycle is a K cycle. Basically, if you want the inverse of say 1, 2 inverse, it's just 1, 2. 1, 2, 3 inverse. It's just 1, 3, 2, right? Yeah. Yes, sir.
So that's G then.
Yeah.
What was the
Quotient. This is a name. Just called G by N, basically. Okay, G modulo N. Right? I mean, there's another name factor group, but we'll see why the terminology. Yes. Sigma, in a sense, yeah. Permutation. Okay. Now, if you want to take the inverse of A1, A2 to AK, how do you do that? well, you can say this is just inverse, it's just A1, AK minus 1, and then A2, right? Yeah. The inverse of this one is this one. Right, so the inverse of 1, 2, 3, 4 is 1, 4. Or you can just put it as 4, 3, right? Multiply them together, you get the identity. Okay. When 1 goes to 2, the inverse 2 will go to 1. 2 goes to 3, under the inverse 3 will go to 2. 3 goes to 4, 4 goes to 3. Okay. Great. Now, yeah. Now you have seen your assignment in your previous one. Any sigma can be written as a product of disjoint cycles. Basically, I mean, you know what you can. So, if sigma as I say 1, 2, 3, 4, 5, then 3, 2, 1, 5, 4. Now you can write sigma as 1 goes to 3. 2. Okay. All of these cycles are disjoint. Right. There's a small like preview on like SN. So all of these cycles are disjoint. People attending, can you see? Can you read the? Can you see the board? Yoo-hoo. Great. Yes. Great. Thanks. Okay. So disjoint cycles. Now, a thing with disjoint cycles, if disjoint cycles commute, disjoint cycles commute. Also, it's not very hard to check. You need 1, 3, 4, 5. That's example. 1, 3, 4, 5 is equal to 4, 5. Right? Look at what happens to 1 under this function. 1 goes to 3 here, and then 1 goes to 3. Okay? Great. Okay, everyone? Pretty good? So now, in your assignment, you have to prove something. Suppose sigma is equal to sigma 1, sigma 2, up to sigma k, where sigma 1, sigma k are disjoint cycles. Length of perspective length. L1 up to Lk. Then the order of sigma is equal to the LCM of L1 up to Lk. Example. For example, 1, 2, 3, 4, 5. What's the order of this? Are these two cycles disjoint or not? Are these two cycles disjoint? So what is the order of this? Is the LCM of the length. What is the length of this one? The length of this one is 3. The length of this one is 2, right? So it has order LCM 3, 2, which is 6. Okay, so this one. 1, 2, 3, 4. What is the order of 1, 2, 3, 4? It's the LCM. Are these cycles disjoint? Yeah. Now what is the, so I can apply the result here. So it's LCM of 2 and 2, which is 2 as order. Now you know what you need. Do you want me to do it? Do you want to do the calculation to convince this order to? I think you can see that. Do you want me to do it? Should I do the calculation? I mean, 1, 2, 3, 4 times 1, 2, 3, 4. Let's do it from the basics. 1 will go to 2, and 2 will go to 1. So 1 will go to 1. 2 will go to 1, and 1 will go to 2. So 2 will go to 3 will go to 4. 4 will go to 3. That's it. Okay. But pay attention. The cycles are not disjoint. This doesn't hold. If you take 1, 2, 1, 3, it doesn't have order 2 because the cycles are not disjoint. This is just 1, 3, 2. That's order 3. Okay, so pay attention. The cycles are not disjoint. This one. Okay. Great. You on symmetric groups, how to compute things. Okay. Now we'll just start with something new. The sign of the permutation. A transposition is a two-cycle. Example 1, 2, 3, 4, 5, 6, right? Any cycle of length 2 is called a transposition. Okay? So what's the order of a transposition? The order of a transposition is what? It's 2, right? 1, 3 times 1, 3 is just the identity, right? Everybody, are we good with this? Yeah. Okay. So transposition is a two-side. Basically, you only flip 2 and you keep the rest fixed. Right? Great. Okay, now another definition. Oh, well. Here, prop. Every sigma in Sn can be written as a product of transpositions. First, prove it for cycles. First, we prove any cycle can be written as a product of transposition. This of transpositions. You see this? It's not bad. Even the exceed, right? Really, it's this one. Like you take, for example, well, 1, 2, 3. What would that be equal to? It's equal to 1, 3, 1, 2. Right? 1 goes to 2 and 2 stays fixed, right? Now take any k cycle, A1, AK, and do the same thing. By induction, really, what you can do is just, this is just A1, AK. A1, AK minus 1, up until A1, AK. So basically 1, 2, 3, 4. It's just 1, 4, 1, 3, 1, 2. Okay. Yes.
How do you get the ladder, like the iteration to from A1 and A1, like?
Oh, okay, yeah. Okay, so the idea is that you want transpositions, okay? So the idea is that you don't want A2 to appear. once it appears here, you don't want it to appear. Okay, so your A1 goes to A2 and A2 stays fixed. So A1 goes to A2. Now A2 next time it will appear here. Sorry, no, it will appear here, right? Then A2. Then A2, what happens to A2? Well, it will appear somewhere. Oh, definitely it will appear. Let's see. A1 goes to A2.
A1.
Yeah, exactly. A2 goes to A1 and A1 goes to. This is the idea.
Because you want like any AI to go to AI plus one.
Exactly. That's right. Okay. Great. So any cycle can be written as a product of transposition. Now let sigma be an ascent. Then sigma can be written as a product of disjoint cycles. And each cycle is a product of transpositions. So really, each cycle can be written as a product of positions. So basically, hence sigma is a product of transposition. And sigma can be written as a product of transposition. Let's give an example. Let's say 1, 2, 3, 4, 5, 6, 7. Okay, how do I write this as a product of transpositions? I can write 1, 2, 3 as 1, 3, 1, 2, and 4, 5, 6, 7. All right, as 4, 7, 4, 6, 4. Okay. So any sigma really, I can write it as a product of transposition. Okay. Great. Now another definition. Sine. This is about the sign of a permutation. This is the definition of the sign, or signature of a permutation. All of this to lead to this definition. Okay. Let sigma be an Sn. And suppose that sigma can be written as a product of, let's see, what's a good letter of K transposition. The sign of sigma written by sigma is just -1 to the K. Okay. Here, sign of sigma is equal to 1, basically K is even. To say that sigma is even. Sigma is equal to -1. Basically, sigma can be written as a product of an odd number of transposition. K is odd. You say. Okay. Now, if there is a small thing here, I'll get back to this later. This definition, or this the sign is well defined. Sure.
Sigma itself is a transposition.
Yeah. What is it? Even or odd? So it's a product of one transposition, right? Okay, it's odd. So if sigma is a transposition, okay, the sign is well defined. I will get back to this later. There's a problem with this definition. Technically, you have to check something. Okay, but we'll get yes.
That
That's the point. That's not true. That is not true. But this definition still makes sense. That's the point here. That any sigma cannot be written unique as a product of transposition. So this K might change. So take the identity, for example, you can write it as 1, 2 times 1, 2, right? Now take the identity as well. You write it as 1, 2 times 1, 2, that's 3, 4 times 3, 4. Right? Now the K changes here. The K is changing. But is -1 to the K changing? No. Okay? This is an important thing. Yes.
Is there a way to prove that identity cannot have a product of 3 transpositions?
Yes. In your homework.
Why?
Okay. In your next homework, you have to prove it. Okay. So that the identity, if the identity can be written as a product of transpositions, then the number of transpositions must be even. Okay. And then if any okay, then I'll write this later. Or maybe I can write it down. Next homework, you have to prove this. Here. Let sigma be an SN. And suppose that sigma can be written as a product of even. You can change even to odd of n even number of transpositions. Okay, of an even number of transpositions. Then any product of transpositions equaling sigma must okay even if it's odd, it can be odd an even number okay, example, the identity is 1, 2 times 1, 2. Now, can you write the identity another way? Yes, you can. But the parity of K doesn't change. Let's do one here. Let's take 1, 2. You can write it as 1, 2. You can write it as 1, 2 times 1, 2 times 1, 2, right? And you can write it as 1, 2 times 1, 2 times 1, 2. 3, 4 times 3, 4. Okay? So the number, if you can write sigma as a not number of transpositions, then you cannot write it as an even number. That's a very good. Yeah. Okay, this is the key part. That checking that this function is a well-defined function, right? If the parity of k doesn't change, then -1 to the k does not change, right? This is the goal. Okay, great. You have to do this in your homework. I think the book does 2 cases, and the homework has 1 case, and you have to do 1 case. So basically, I tell you to read the 2 cases in the book, and then the other case just follows in the same idea. Okay, great. Yeah. Okay. Now, sine of sigma tau property. Sine of sigma tau. So let sigma and tau be the same. Let sigma tau be the same. Sine of sigma tau. The sine of sigma sine tau. Let's prove this. So suppose sigma can be written as a product. Let's say k transpositions. Not too much better, but anyways. And I suppose that tau can be written as a product of L transpositions. Right? Sigma can be written as a product of K transposition. Tau can be written as a product of L transpositions. So when you put them together, you get K plus L transpositions, right? K transposition from sigma, L transposition from tau. Put them together, combine them together, you get K plus L transpositions. Sigma tau, hence sigma tau can be written as the product of L plus K transposition. Okay, so the sign of sigma tau is -1 to the L plus K, which is -1 to the L, is -1 to the K, which is sine of sigma. Okay, so sigma can be written as K transpositions, and tau can be written as L transposition. Just put them together, right? 1, 2, 3, 4, 5, 6, say 3 transpositions, 3 transpositions. This is just 1, 3, 1, 2. Sorry, 2 transpositions, 2 transpositions. So 1, 3, 1, 2, 4, 6. Okay. Okay. That clear? Great. Now, the sine of the K cycle, the sine of A1 to AK, this is just what is that? So what is the sine of the 3 cycle? 3 cycle is, so what is the sine of a transposition of a 2 cycle is? 1 is odd. It's -1, right? You can write the transposition as a product of 1 transposition. Right? So the sine of 1, 2, -1. Now what is the sine of 1, 2, 3? 1, 2, 3, you can write it as 1, 3, 1, 2. An even number of transpositions, so this is just -1 for you, which is 1. Okay? Now sine of 1, 2, 3, 4. This is just sine of 1, 4, 1, 3, 1, 2. What is that? Is it just -1, 3? Just -1. So the sine of a K cycle, what is that? This is just -1 to the K plus 1. or minus 1 to the k. So a cycle of even length is an odd permutation, and a cycle of odd length is an even permutation. Okay? So if you have a cycle of even length, 1, 2, 3, 4, it's an odd permutation, has sign -1. And if you have a sign of odd length, say 1, 2, 3, it has sign 1. Okay. Great. Now I asked, let's do a small exercise using this fact, this multiplicative property. So find the sign of 1, 2, 3, 4, 5, 6, 7, 8, 4, 5. Now to find the sign of a permutation, you don't really need the. Let's put here. Let's put 8. You don't really need the cycles to be disjoint. Okay. The sign is multiplicative, basically. Okay, so what's the sign of a tree cycle? Is it even or 1? The cycle of a cycle of odd length is
Even.
1. Exactly. So a permutation, a cycle, a k cycle, if k is odd, is even. So this is sign 1. This, what is the sign of this? 3 cycle is 1. 2 cycle is -1. -1. Take the product of these, what do you get? 1. So the sign of this is equal to. Okay? This is how we do it. Now, sign of sigma inverse. Sigma inverse is equal to sine of sigma. Let's prove this. Sigma as a product. Sigma 1, sigma 2, sigma k of disjoint cycles.
Wouldn't it be simpler to do sine of sigma inverse that would do the sign of the identity, which is even, meaning that from there you can directly show that
That's very good. That's very, very good. Yes, thank you. It's very good. Yeah, very good. Very, very.
that looks
very
so
good.
much easier. So.
It is.
Okay.
Sine of sigma inverse is equal to the sine of sigma. Let's prove that. Sine of sigma inverse times sigma, the sign of the identity, which is 1. Now, sine of sigma inverse is multiplicative. Sine sigma is equal to 1. Right? Now, 1 over sine of sigma is the same thing, right? 1 over plus or minus 1 is the same thing. The sine of sigma inverse is 1 over sine of sigma, which is sine of sigma. Since 1 over minus 1 to the k, just minus 1 to the k, right? Okay, great. Now, what time is it? 11:08. Okay. AN is the sigma in Sn, such that sine of sigma is 1. It's called the alternating group. Index. Now claim AN is a subgroup Sn. And well, let's prove first of all. AN is not proof of SM. This is clear, right? So the identity, the sign of the identity is 1. The identity belongs to AN. Now let's sigma tau belongs to AN. Then sine of sigma is equal to sine of tau is equal to 1. So sine of sigma tau is equal to sine of sigma. Sine of tau is equal to 1, right? So sigma tau belongs to AN. Let sigma belong to AN. Let sigma belong to AN. We know that sine of sigma inverse is equal to the sine of sigma is equal to 1. Give me inverse n. So AN is a subgroup of SM. Okay. Now I claim that AN has half of the elements as S2 and as answer. N factorial over 2. Okay, well, let's say that the cardinality of AN is N factorial over 4 and bigger or equal to. Okay. Proof. And we'll see another way of doing that later on, but this is what we can do with the knowledge we have. So let sigma, let's say tau, be an odd permutation in SM. Pick your favorite odd permutation. Let's say 1, 2. Define F AN for Sn minus AN that takes an even permutation sigma to tau times sigma. So if sigma is even, then an odd times even is what? Minus 1 times 1 is minus 1. So odd times even is odd. So really, tau sigma will belong to Sn minus AN. So F is a bijection. Should I prove this or just clear? Is it clear or should I let?
I mean, we can just put the tau inverse in front and that's it.
Exactly. So to prove F is injective, right? If F is so injectivity. If F of sigma 1 is equal to F of sigma 2, and tau sigma 1 is equal to tau sigma 2, and sigma 1 is equal to sigma 2. Now, surjectivity. So let I don't know, let's call it alpha, say it's a bad name. Let alpha be in Sn minus N. So alpha is an odd relation. Then tau inverse alpha. Tau inverse is odd. Alpha is odd. Odd times odd is minus 1 times minus 1 is even. Right? Is even. Tau inverse alpha belongs to An. And what is F tau inverse alpha? Is equal to tau inverse. Okay, great. Hence, well, the cardinality of An is equal to the cardinality of Sn minus An. But I know that the cardinality of Sn is equal to the cardinality of An. So this is just 2 times An. We can take out An. So the cardinality of An just is N over 2 is N factorial over 2. Okay. Now there's a theorem that we will not prove. It's not that the proof is beyond this course, but it's a bit tedious. But you can use the result when you need to. And I will let you know when you can use the result. Okay. Now An theorem, let n be bigger or equal to 5, then An is a simple loop. Okay, so basically An has no normal subgroups except the identity and An itself. Okay, now the proof, you can look at the book. Chapter 10. Right, it's a definitely you can use this result without proof. You can quote it if you need to, and you can read the proof. Okay, great. Now let's do this. What time is it? I need to talk about the midterm as well. What time is it?
It's
What?
11:16.
Okay. Okay, so book chapter 10. Now let's write down the elements of A3. What is A3 really? A3 is just you have S3 and you take all the even permutations. So A3 is just the identity 1, 2, 3, and 1, 3. A4. What is A4? How many elements does A4 have? S4 has 24 elements, so A4 has 12 elements. Let's write them down. So you have all the 3 cycles, right? 1, 2, 3, 1, 3, 2. Oh man. Then you have 1, 2, 4. And you have 1, 4, 2. How many 1, 2? Okay, I have a few more. Then you have 1, 3, 4. Then 1, 4. And then you have 2, 3, 4. 2, 3, 4. Then you have 2, 4, 3. I have 1, 2, 4. I have 2, 4, 3. 1, 2, 3. What else do I need? 1, 2, 3, 4, 6, 7, 8. Yeah. And then you have 1, 2, 3, 4. 1, 4. 2, 3. And what as well? You have one more, 1, 3. This is A4. Now in your homework, you have to show that A4 has no subgroup of order 6. Again, I guide you through it. The answer should be like 1 small line and 1 small line. Okay? I mean, the book does it, but it's a bit long. But I try to guide you through it today in 2 parts. The first part is 1 line, the other part is 1 line.
If we take more than 1 line, is it a problem?
No, I mean, it should be quick. That's what I mean. You should not write pages. Okay? So A4 has no subgroup of order 6. Oops. Right? The proof is not that bad. Okay, now I'll introduce, okay, this is for the alternating groups, the symmetric and alternating groups. Now I'll use the diagonal group. I think I have 5 more minutes. I'll introduce them. Consider a square of the group D3. Well, consider an equilateral triangle. Which I'll call 1, 2. Okay, that looks everything. Okay, now what are the symmetries of this triangle? What are the symmetries that preserve this triangle? If you rotate everything by 60 degrees counterclockwise, Does that preserve it or not? Yeah. What time? I mean, this is not part of the midterm material. Okay, so I'll just talk about the midterm. Unless you want me to finish this. You're not interested in finishing this. Okay, so we'll continue this next time. Okay, so I'll continue technical group next time. Technical group is not covered on the midterm. So, okay, so I'll talk about the midterm. So the midterm has 4 questions.
That's so few.
Whoa, it's only 50 minutes.
50 minutes, 4 questions. Now, questions have parts. Some questions have parts. Now, I've been told by Julian, William, and Alban that it's a bit long. It might be a bit long, but we'll just deal with that. Okay? You can finish in 50 minutes. I am very confident that if you study, you can finish everything in 50 minutes. Now, the thing is, all the questions are questions you have seen. There is nothing new at all. Nothing new. Okay, yeah, no. Sorry, yeah, there. Yeah. Of course. Yeah. Yes. Yeah. So again, so what you have to do is the questions in the tutorials, the question in the notes, and the question in the homework. So everything you would have seen so far. So the notes are important. I will ask you proofs from the notes. Okay? You have to do the proofs from the notes. I will ask you proofs from the assignments. I will ask, like, you will see an assignment question that is exactly there. You have to know every single thing. Okay? So really every single thing. Everything are things you have seen. I mean, I wrote the solution. I wrote it and I wrote the solution. The solution can fit on 1 page of text of LaTeX. Okay, so all the answers you should not be writing a lot. Okay, so the first question is a Euclidean algorithm question. I mean, I can tell you the first question. The first question: use the Euclidean algorithm to find the GCD of 2 numbers. And the second question: express the GCD as a linear combination. This is the first question, 25 marks. And I've had like big numbers. They told me it's a bit stressful in 50 minutes to deal with big numbers. So I reduced it to 2-digit numbers. Okay, the 2 numbers are 2 digits. And even those numbers are numbers we have seen in class or in the assignment or in tutorial. So like, I just made it like as easy as possible. That's 25 marks. The second question, well, the second and third questions all have parts. But again, you should not be writing a lot. Okay, you should know the statements of the theorem. I can tell you state Lagrange's theorem. If G is a finite group and H is a finite and H is a subgroup, then the number of elements of H divides the number of elements of G. That's, for example, that would be on 5 marks. Very easy. Then I can ask you, use Lagrange to prove something else. Okay, things like that. Fermat's theorem, Euler's theorem, you should know how to prove them. All of these I've done in class. So really the midterm is just a test if you were present in class, if you were doing the homeworks. And yeah, so that's it. I mean, again, you have 19 days left, right? 19, 20, what, we're the 12, 11? You have 19 days.
But it's until the 23rd.
No, it's until, so I said it's until the 18th. Now the 18th is the reading week. Okay, so I said it's until the 18th, but 14 to 18 is reading week. So I put it to 11. So the midterm stops today. The material of the midterm stops today. Okay, so that you can study how many lectures we've had so far, 20 lectures, 19, 20, I don't know. You can you have to study all of the lectures, you have to study all the theorems and all the proofs and all the assignments. Again, every single, pardon me?
Until what point?
Until today.
Even what we did today.
Yes. No, I mean, I don't think you get that in other classes, right? You don't get a midterm that stops 19 days before.
Yes.
And we also don't have midterm that's only finishing 15 minutes.
Yeah, but again, the final's not going to be like that. The finals, you will see new questions, and the final's not going to be just bookwork. Yes, sir. Both are fair game. Both are, you will have, so yeah, I said at the beginning that an ungraded question will appear. And that has happened already. So there is a question that is not graded that will appear. And it covers the assignments until this one, until the ones I'm going to release today. Yes, the one I'm going to release today is due the 25th. Okay. So again, I'm giving you, and the one that is due today, you can hand it in 1 week late with no penalty. Yes. No, this one is included. Assignment 6 I released today. Yeah, it's included. Okay, so please take the break as an opportunity to study everything. Just be sure not to forget it after like 19 days. Okay, great. Good luck, everybody, and have a very good break.